Thank you for the nice introduction and welcome to our talk about washing machines and other household appliances. Just to be clear, when we say household appliances, we are not just talking about washing machines. We mean dryers, dishwashers, ovens, microwaves, coffee machines, and all these things. Millions of these appliances are sold every year, and almost everybody has one of them at home. But at least to our knowledge, nobody has done research on these machines. But that's exactly what we want to change today. To do research on these machines, in many cases, you need to open them up. That's actually pretty easy. You just undo two screws at the top and slide the cover off. It's very similar to open a PC case. And once you look inside, it's quite different. Here on the front side, you see the display module, and on the right side, you see what's called the power module. And then there are quite a lot of cables and, of course, a lot of mechanical parts as well. But now that you can see this, we want to point out our first warning. These devices contain high voltages everywhere, usually without isolation. Sometimes there are low voltages cable, but even those may or may not be galvanically isolated from Earth. So if you are working on these machines, you must take proper safety precautions, like using optocouplers or isolating transformers and the like. And one thing you should never do, connect your computer directly to such an appliance. Very important. You will kill yourself. The second thing is, what's also very different from working with the PC case is that household devices usually have water in them. They generate heat and steam. They shake and they vibrate and they have rotating parts. And here in this short movie, Severin shows in a truly brave experience what happens if you disable all the security bits in the firmware. So you can definitely flood your house. Credits to Severin for this truly brave experiment. And the third warning, and that's the last warning, but probably the most important warning, the household appliances are usually actively used by family members. Reverse engineering these machines can temporarily make them unusable, and that can lead to serious problems with your family. I can tell you from my own expertise. So it's definitely a good idea to start with some spare parts taken from broken devices. This is what I call my first lab setup, a very professional lab setup, as you see. And in the end, I ended with something like this. I call it a dishwasher in a box. That's all the important non-mechanical parts of a dishwasher, all the cabling and power module, and so I will tell you later. After this warning, we can have fun with the details, and Severin starts with the Miele research.
Well, thank you, Hajo. So I did some research on Miele appliances, and this research started with a very old washing machine from my parents, which suddenly stopped working after 20 years of operation. Now, after doing some regular maintenance on that machine, it seemingly started to work again, but the machine would always stop before the final spin cycle, which is very annoying. Now, I did some online research and I found out that there's a little sensor inside this machine which measures the water level, and if this sensor gives false readings, the machine won't start spinning. Now, a potential fix for this problem is to calibrate the sensor. But unfortunately, calibration cannot be done through the integrated service menu of this machine, but it requires a special software from Miele, which is known as the Miele Diagnostic Utility, or MDU for short. Now, this is a proprietary tool which requires a license from Miele and can only be used by service technicians. Now, I found this nice screenshot in a forum post, so let's take a closer look at what this software can do. So we can see in this screenshot we are connected to a washing machine with a certain software ID, and we have access to a bunch of different properties. So for example, we can take a look at the sensor values of the machine, like the water level, temperature, motor speed, and also the set points for these values. We have access to the operational state, the relay state of the machine, the program settings, and we are also able to make corrections to the built-in washing programs, in addition to being able to calibrate the internal sensors of this machine. Now, how does the MDU actually work? Well, we obviously need some kind of diagnostic port on the appliance side, but as we've already heard in the introduction, the electronics inside these machines are often not galvanically isolated from mains voltage. But Miele has a solution for this, which they call the optical interface. And in fact, it can be found on the front panel of this washing machine right here next to the inlet fault indicator. Now, this is actually a bidirectional optical port. Now, this optical interface is not specific to washing machines. In fact, it's present on almost all Miele appliances since 1996. So you have this on dishwashers, on dryers, on stoves, on kitchen hoods, on fridges, and as I recently learned, even on wine cabinets for some reason. Now, on older appliances, it's quite easy to find because it's most often next to a small program correction or PC label. On newer appliances, as you can see, it's oftentimes very hard to find. Now, this interface is not only used for the customer service, but also during device development at Miele and during end-of-line testing in manufacturing. Now, to communicate with this interface, you need some special hardware for service technicians. This hardware consists of this interface box, which connects to your PC using USB, and a head unit, which is attached to the front panel of your machine with a little suction cup mechanism. And right next to that suction cup, you can see an optical transceiver. Now, little is known about this optical interface if you do some online research, so I decided, well, let's see if we can hack this optical interface. Now, because working on real appliances is pretty dangerous, I decided to go on eBay and buy myself a control board from an early 2000s Miele washing machine. Now, the cool thing about this specific board is that the power electronics are actually separate, which means it's pretty safe to work with. And we also have some technical documentation available for these older boards. So the connector printouts, for example, can be found online. Now, the main components of this board are a Miele-branded microcontroller, which actually turns out to be made by Mitsubishi. And it has an instruction set very similar to the famous 6502 or the successor, the 65C02. Now, normally I would just go ahead, dump the flash memory, and start reverse engineering from here. But unfortunately, it turns out this chip is from the 1980s, and it contains a mask ROM instead of flash, which means to get access to this mask ROM, we would have to physically take this chip apart, which I didn't want to do. So we have to continue without access to the firmware. Now, the optical interface, you can see that one in the bottom right corner, right next to one of the regular indicator LEDs. You can see it looks a bit different because it contains not only a red LED, but also an infrared receiver in the same package. Now, this optical interface then communicates with the microcontroller using UART. But unfortunately, nothing is sent on this interface on its own, so we cannot really figure out the baud rate. We don't know what kind of protocol it uses, and nobody, as far as I know, has ever attempted to reverse engineer it yet. So I started doing some research again, and I found a project that was initially completely unrelated to this. It's about Miele at Home, which is the official solution for remote appliance control from Miele. And it works by using this communication module that you can attach to your appliance, and it communicates with UART. Now, this Miele at Home thing was reverse engineered by a guy called Michael Scholze, and he posted about his findings online. And it turns out the protocol used by Miele at Home generally looks like this. So you have very simple 5-byte frames with a command byte, 2 parameters, a length, and a checksum. And the UART is configured for 2400 baud with no parity. So I thought, well, this sounds like something that might have been developed in the 1990s, and it might even be the diagnostic protocol we are looking at. So I decided to just send this frame that we saw here to our EDPW board, and unfortunately got no response. Now I played around with the UART settings a bit and found out that it actually requires even parity, and then we actually get a response from the board, which includes the software ID. So now we know how the frames are generally structured. We can just try out every single command that is available to us and see if we get a response from the board. Now, we already saw the command hex11, which queries the software ID. And the interesting thing is this command 20 can only be sent after we queried the software ID. So it might be used to unlock further diagnostic commands, just like in automotive diagnostic protocols. For example, you have like a security key that you have to enter before you get access to all the different kinds of diagnostic commands. So command 20 is for unlock interface, command 10 is to lock the interface. But apparently we need to find some kind of specific set of parameters to actually be able to unlock the interface. But since we don't have access to the firmware, let's see if we can find some kind of side channel on this microcontroller. Now it turns out this microcontroller has some extra pins for the so-called microprocessor mode with external memory. And these pins are unused in our case. But they're still active. And one of these pins is especially interesting. That's the sync pin, which is always high when the microcontroller fetches an instruction from its internal ROM. And figuring out the exact instructions that the microprocessor is running would be pretty hard, but we might be able to use this for a timing attack. So let's see what the sync trace looks like if we send a valid diagnostic command and if we send an unknown diagnostic command. And as we can see, the length of this response is completely different. Now the unlock command on the firmware side is probably implemented something like this. So we are dealing with an 8-bit microcontroller, which means these 2 parameters are checked sequentially. And if the first value is guessed correctly, the execution time of this subroutine will change. And we are able to measure the execution time difference by taking a look at the sync pin. Now, another advantage of this timing attack is that we only need like at most 512 iterations to find the secret key. So this is exactly what I did. I wrote a quick Python script which just tries out every single value for the first parameter. And as we can see, the response we get on the sync trace is in almost all cases identical, but there's one case where it is slightly longer, and this is exactly the kind of parameter value that we are looking for. Now we can repeat the same procedure for the second parameter, and once we do this, we have the correct parameter values to unlock the diagnostic interface. Now I decided to call this specific set of parameters the diagnostic key. If we unlock the interface, we suddenly have access to 2 more commands. One of these is used to read from EEPROM, and the other one is used to read from memory. And both of these accept a 16-bit address. Now, it turns out this read memory command is not only limited to reading from RAM, but we also have access to the mask ROM, which means we are able to dump the full firmware from the device, which is exactly what I did. I just hooked up a USB UART adapter. As you can see, the interface is flashing, and in around 30 minutes, we are able to dump the full firmware from the device. Now that we have the firmware, we can take a look at the full command set of the diagnostic protocol, because it turns out there's not only one security level, but actually 2 levels, and we can unlock the second level using another unlock command with a different key. Now this gives us access to another set of commands that can, for example, be used to write to memory or EEPROM. We can jump to arbitrary subroutines. We can put the device into an infinite loop using the halt command, and we can increase the baud rate. So this interface basically gives us like full debug capabilities. Now that we tried this on a control board, let's see if this also works on a real appliance. Now to do this, we need some kind of optical communication adapter, which is relatively easy to build. We need an ESP32, a special optical transceiver from Osram, and 2 resistors wired up like this. And then you end up with something like this, which costs like less than 10 euros to make. Now we can stick this adapter to a washing machine. This is the one that we saw in the beginning. And the first step is now to find out the diagnostic keys for this device, because it turns out these keys are not identical. They are, in fact, model-specific. But since we know how the protocol works, we can use a simple brute force search, and we get 2 keys in like 30 minutes. Now, let's see if we can also dump the firmware. But, well, unfortunately, the reading process always stops at a certain address, which turns out to be exactly where the firmware section starts. So the firmware basically has like a ROM readout protection built in. Now, it's pretty easy to bypass this ROM readout protection because we essentially have like read, write, and execute access to memory with the diagnostic protocol, which means we can just write our own dump subroutine. And it works like this. So we halt the firmware execution, we write the subroutine into an unused part of the RAM, and then we just jump to the subroutine. And what the subroutine does, it just goes through memory and just writes out the memory contents to UART, and UART is connected to the optical interface, and we get a full firmware dump. Now let's take a look at how this ROM readout protection is actually implemented. It's pretty simple. It just checks the read address if you send a read command. But as we can see, before doing that, there's a flag that can be set, the protection disabled flag. And if we set the first bit of that, this readout protection is completely disabled. So we can just like dump the memory the usual way. Now let's take a look at a different example. This time a Miele dishwasher. Let's see if we can find the diagnostic keys. There they are. Now I decided to put these diagnostic keys in decimal form on this slide. Now does any one of you know what these 2 values might be in hexadecimal format? Like any guess? So the first value turns out to be hex 1, 2, 3, 4. And the second value is 5, 6, 7, 8. So yeah, really creative. Okay, next step, dumping memory. Same as before, ROM protection can be disabled again by setting this flag to the value 2. Now I decided to turn this research into an open source diagnostic tool for Miele appliances, which I call FreeMDU. Now, FreeMDU is basically a collection of different tools. So we have a protocol library, a terminal UI application, and some experimental smart home integration for Miele appliances. Now this FreeMDU library is basically just a simple implementation of the diagnostic protocol with simple appliance wrappers for the different washing machine models. Now, if we want to read these diagnostic properties like the program phase, water level, temperature, and so on, we basically need a memory map to know where these properties are stored in memory, because these memory locations are different for different models of Miele devices. And using this library, we can build ourselves a very simple terminal UI application. It's cross-platform, and it essentially provides almost the exact same functionality as the official MDU software. So we can take a look at the sensor state, the failure information, operating state, and we are also able to trigger actions on these devices. So for example, we can start washing programs, we can set program options, but please be careful here because, for example, if you set program options, the machine does not perform any validation on these options. So you could, for example, choose the drain program and enable the water plus option, which makes no sense at all, but it's possible. But please don't try this. I also wrote a experimental smart home integration with an ESP32, which is also pretty simple to use. It requires like no configuration at all because it supports Home Assistant's auto discovery protocol, and you can simply integrate your washing machine or your dishwasher into Home Assistant. You have access to all the operational state of the machine, and you can also trigger actions like starting the washing program on machines. So now we only have a few final questions left. Like, we haven't talked about how program corrections work yet. I would appreciate some help on that. I'm still working on that, but if any one of you is interested in that, please contact me. Now, what about more recent appliances? Well, unfortunately, it turns out they use a new diagnostic protocol, but they still have the optical interface. And this new protocol uses a challenge response authentication with XOR and a static key that is identical for every Miele appliance out there, which seems kind of pointless to me, but yeah, I digress. Now, final question, did I actually manage to calibrate the water level sensor on my parents' washing machine? Well, the answer is no, but the washing machine is working again for some reason. Thank you. So Hajo is going to tell you a bit more about BSH devices now.
Thanks, Erin, for your great insights. As you said, I've been focusing on BSH devices. BSH is one of the biggest producers of household appliances worldwide. But many people might not immediately recognize the name because BSH is better known through its brand names Bosch, Siemens, Gaggenau, Neff, and many others. When I first started digging into these devices, I came across a patent describing how the individual modules inside an appliance communicate over a bus system called D-Bus or D-Bus2. But because it's a proprietary bus, there's no public documentation available anywhere. Once you know that there's a D-Bus or D-Bus2 somewhere inside the machine, the question is, where is it exactly? Here you see the power module extracted from a dishwasher, and at first you are basically lost. Lots of colorful wires, different connector types, and absolutely no labels or anything else that could help you. It turns out that the connectors in household appliances are usually so-called RAST connectors. This type of connector is used by pretty much every appliance manufacturer, at least in Europe. And D-Bus connectors are often 3 or 4-pin RAST connectors. But beware, not every 3 or 4-pin RAST connector is a D-Bus connector. It's more like a higher chance. A very helpful tip is to look at the slots on the main board. They usually have coding lugs, and if you see 2 or 3 slots with the same coding side by side, that's a strong hint that it could be a D-Bus, because with the bus, it generally doesn't matter which slot you plug into. But there's no strict rule. You always have to double check. And the D-Bus connector has at least 3 wires. That's ground, data, and bus voltage. But the order is important. On the power boards, the sequence is ground, data, and bus voltage. But on all the connected sensors or control components, it's reversed. It's bus voltage, data, and ground. And the bus voltage is 9 volts in washing machines and 13.5 volts in dishwashers and dryers. And the data pin carries a 5-volt signal. And when you know all this, you can verify quite reliably whether you are dealing with a D-Bus or some other random cabling. Now let's take a look at what the D-Bus is actually used for inside household appliances. For example, in a washing machine, at least the control board is connected to the D-Bus as well as the user interface. That's probably how BSH started introducing the D-Bus in the early 2000s. But over the years, they added more components. First, the unbalanced sensor, then in newer machines, the motor controller, and in the latest generation, even the Wi-Fi connection module. And for dishwasher, it looks quite similar. Again, the control board and the user interface on the D-bus, but also the time light module. That's a little projector that shines the remaining time onto the floor. And of course, the Wi-Fi connection module as well. It is quite important to mention that many components are not on the D-bus. Things like the door sensor or the heating elements, the pumps and the valves are still wired in a more traditional way directly to the power board. To make the flow of D-bus messages a little bit easier to understand, let's walk through a simple example. Imagine a washing machine where we only look at the two components, the user interface panel and the power module. And when you press the temperature button on the user interface, the panel sends a frame to the power module. This frame contains here, command is 1004, which translates to something like set temperature. And it has an argument of 4, which corresponds to 60 degrees in this case. Then the power module processes this frame, recalculates things like the new total program time, and sends back updated information to the control panel. The response is a packet with command 1600, and the argument is hex 60, which represents 1 hour and 63 minutes. Of course, you can also manually send these things, like you can see here, on the bus, and the display will just display it. A second example is this time involving the power module and the unbalanced sensor. The unbalanced sensor is really important for a washing machine. If your clothes aren't evenly distributed in the drum and it spins at 1000 RPM, the whole machine could start hopping around the room. You surely do not want that to happen. So when the power module starts spinning the drum, it first sends a frame to the unbalanced sensor, which this time a command 4002, which is something like start measurement, and one of the argument is 19 hex, which is like 25 seconds measurement duration. And then the unbalanced sensor receives this frame and immediately starts to measure the drum's behavior. It sends back the results with command 4010, which contains 3 signed integers representing the directions and the magnitude of the unbalance. And if the unbalance is too high, the drum speed is reduced and the laundry is redistributed using a clever algorithm. To sum it up, here are some comments we have observed to the washing control unit, something like set temperature, set wash program, set spin speed, and options like wrinkle-free or free wash, which are encoded as feature bits. And then from the control unit to the display to set the remaining wash time or the door status and program status and other things. And then also the comments I showed you before between the unbalanced sensor and the control unit. But how is data actually transmitted on the D-bus? The D-bus is a multi-master serial bus that operates at 9600 baud and uses standard UART data framing. And each frame follows a simple structure. It starts with a length byte, then an address byte. In the upper nibble, it encodes the target device address, and in the lower nibble, it encodes the subsystem within the target. And then a variable number of data bytes follows, and in the end, we have a 2-byte checksum. And when you dig a bit deeper into these frames, you will notice that the first 2 bytes of the message have a special meaning. I call it the command word, and it basically defines what action the target should perform when it receives this frame. So to sum it up, this frame here can be translated to process command 4002 on subsystem 7 of node 4 with a payload of 178090. And When the destination node successfully receives this frame from the dbus, it acknowledges this frame by sending back a single acknowledgement byte, which is calculated with the destination address in the upper nibble. And in the lower nibble, it's always the letter A, which probably just stands for acknowledgement, I think. So once you know all this, it's tempting to sniff the bus and feed the data into your home automation system without any cloud involvement. But of course, you need some hardware for that. So I started with this something, which is just an ESP chip and a simple DC-DC converter. It works, but it's not recommended to use. And then I started with a second generation thing, which added an open drain level shifter that has the advantage to allow proper bus writing as well, but it's still ugly and experimental. So obviously, as you can see, I'm not an electrical engineer. So if you have PCB design skills, so please help me to build a better thing here. And so on the software side, I built an ESP Home extensions that's really easy to use. You simply define a set of sensors that react to specific destination addresses and commands on the bus. And in this example, you can see how the x-axis value of the unbalanced sensor is assigned to a sensor value in Home Assistant. So this is what it looks in the end. You get all the standard information, but you also get diagnostic details you normally wouldn't see on the control panel. For example, the unbalanced sensor readings or which internal program module is currently handling the washing program. And on newer washing machines, you can even see the exact drum rotation speed in real time. So to sum it up, if you want to integrate your own appliance into your home automation, there's one key rule. Each appliance type has its own set of dbus commands. So dishwashers, microwaves, fridges, wine coolers, coffee machines, and they all seem to use the dbus. But the commands and the arguments and the request-response logic strongly varies. I think that every department at BSH has its own creative way to craft new commands for the devices they build, but I don't know. It's when you look at the bus, it seems so. But fortunately, some users have contributed their findings from appliances they own, and feel free to add more to my GitHub repo if you want. So we have done the home automation thing, but what's next? So one user noticed that the power board of a dishwasher has a 6-pin header in the lower left corner. That's worth investigating, and it turns to be out an ST-Link connector, which you can hook up using a cheap ST-Link dongle. And even better, the MCU isn't RDP protected, so with OpenOCD you can just dump the firmware, you can step through the code. It's more like working with a dev board. It's pretty good from a reverse engineering side. And if you have the firmware at hand, you will notice some tables that match exactly the dbus commands you observed on the dbus. And the bytes that follow look very much like internal firmware addresses. And it turns out that these lists are part of a way bigger structure, and this structure is describing the subsystems, and all the incoming and outgoing commands are just linked to them. And if you write a simple script, you can build a full list of all subsystems for an appliance, including every incoming and outgoing command and their argument lengths and the handler functions they map to. And so if you're using a disassembler, you can then just quickly jump to the exact location you want to analyze. And that's, of course, from a reverse engineering perspective, very nice as well. And when you go to the list of subsystems, you will notice the subsystem 0, which behaves slightly different from the others, as its commands are usually never seen on the D-bus. So you definitely have to look at this subsystem 0. You notice that two commands, F000 and F001, use the same handler function, and F200 and F201 as well. So it's probably best to reverse engineer them first. And if you look at the decompiled function, you will see that the first function accepts a 16-bit address at argument byte 2 and 3, and while the second command accepts a 32-bit address at bytes 2 to 5. And the rest of the function is essentially the same for the both commands. And if you decompile the rest of the function, it reveals something quite useful. These commands allow you to read and write all memory locations on the module directly over the D-bus, regardless if the MCU is RDP protected or something else. And writing directly to the MCU memory is also nice. Then you can do things like this as well. And the nice thing is subsystem 0 is available on all the components in all devices I've seen so far. So it's quite easy to connect to the D-bus and dump all the firmware from all components you find in all the machines. So let's try this. Try to dump the firmware of the TimeLight module. As I said in the beginning, that's a little projector in dishwashers that shines the remaining program time onto the floor. And that's probably a perfect candidate for firmware dumping. And the first step is always to explore the firmware with a simple visual inspection. I use a fantastic tool for this, which is called Binxel View. And if you load the binary with a pixel width of 8, you will immediately spot the font used to project the remaining time. It's on the right side there. If you increase the width a little bit more, you see a Siemens logo, a little bit more Gaggenau logo. And then you think on the left side, there might be some graphic, but the width is not right again. Now you have to increase it a little bit more. Yeah, that could be a graphic. Okay. I think they have fun working at, must be fun working at BSH. So the challenge for you is find the dbus command to project these graphics onto the floor. I didn't manage so far. If you know how to do it, please contact me. So we have the home automation, we have the firmware dump. What's next? Of course, BSH also offers a cloud service for its product. It's called Home Connect, and this service is implemented via a communication module inside the machine. It's a small black box that connects to the two worlds. It connects on the dbus on one side and to the Wi-Fi network on the other side. And just to say to you that for the BSH cloud, there's an official developer API, which is really great. I suggest you have a look at it. But since we are at the CCC, we want to know if there's a kind of unofficial API for the module as well. So this communication module, it uses the dbus address of B, and it communicates with the power module as at address A. Maybe you noticed the control module usually has address 1, but especially for the COM module, they added a second dbus address A just for the communication with the COM module. And then the control module maintains a parameter list that stores all the possible settings and status values. And that means that the COM module, of course, does not need to sniff the bus. It just asks the control module at address A to send the parameter table, and then it knows the overall status of the appliance. There's also a set of commands for that. It allows the control module to export the table structure and its values to the COM module. And in addition, there are many other commands that let the COM module read or modify individual values via the cloud. After observing all this, I ended up writing a dbus stack. I call it Open Dbus that handles the entire handshake with the COM module. And this way, the module happily thinks that it's talking to a dishwasher rather to an ESP32. And it connects itself to the cloud. And I will here you see the full handshake, and in the end, you see the COM module is correctly initialized. And I will probably publish the stack tomorrow. So. So now we have the home automation, the firmware dump, the COM module, the open dbus stack. But in the end, we have the question when Severin and I met, why are we doing all these things? And then the idea came up. Miele is a great company with great products, and BSH is a great company with great products, but they are competitors. But wouldn't it be great if these two wonderful companies joined forces and formed an even stronger, love-filled cooperation? So we decided to kick off this wonderful cooperation. We took a Miele washing machine. We added Severin's FreeMDU protocol library. Then we built an AMBCL. It's an advanced that's an advanced Miele BSH compatibility layer, and we call it advanced because it was completely generated by AI and not by us too. And on the top of that, we added the Open Dbus stack plus the COM1 module and then the BSH Home Connect app. So we have two worlds connected. So if you open the BSH app, you see correctly the Miele device there. Unfortunately, if I send Miele as a vendor string to the COM module, the app crashes. I think. No, it does not crash. It just does not work. I think BSH does not know of this new cooperation yet. Because we just invented it yesterday when on our train ride to Hamburg. But it's possible to start the machine, the Miele machine, via this app, and it shows the correct serial number from Severin's board. Miele Miele does not have the concept of an FD number, so we had to fill in some default value there. I hope you recognize it. And yeah, we cannot change the model number because then the app also stops working because it cannot load the manuals and other description. So I hope Miele and BSH will connect together, and then they will create an update for the app. So thank you so much.
All right. All right. Thank you for this amazing talk. We now have a few minutes for questions, and they're already, here we go. So, microphone number 2, let's take it.
So I've reverse engineered the Siemens Home Connect app to be able to produce a local only, an offline Home Connect module. And in doing so, the one part I wasn't able to figure out was how the pre-shared key is generated. That my Python library requires that you use Frida to extract it from the app. I'm wondering if you, in reverse engineering the Connect module, if you found where those keys are generated and how they are how they're maintained.
Sorry, I did not get it from acoustic. Perfect. Maybe you can.
Yeah, sorry. Can you repeat the question very briefly?
Did you find where the keys, the pre-shared keys, are used for communication between the Home Connect app and the Wi-Fi module?
Maybe we have to talk about this later. The only thing I can tell you, the COM module has, every COM module has an own set of own keys, which it uses to connect to the cloud, which is, from a security perspective, a really good decision, I think. Maybe we can talk about this later, because I didn't understand you just from acoustic. Sorry.
We'll talk later about it. I've reverse engineered the Home Connect app side of it. So we should talk about how to connect that.
Yeah.
Okay, great. We're going to continue with a question from the internet.
The internet wants to know, with all the knowledge you got about the software, can you use this to modify the programs, to define your own washing programs, to adapt the wine cooler's temperature depending on the weather station outside?
Yeah, so that should be possible theoretically, but so for me, I only looked at older Miele washing machines and dishwashers, so these have very limited possibilities in terms of making changes to the washing programs. So, but I think that would be possible, yeah.
All right, microphone number 4, please take it.
Hi, thanks for the talk. So, did you report to BSH customer support about their app not working with your Miele?
Actually, we got contacted by BSH and both by Miele and BSH when they read about this talk, and we had a really good talk with them. They were quite open, no pressure, no anything. They just wanted to know if everything is safe. And I'm pretty sure that they are watching this talk, and maybe they can do an update for the app, yes.
Another question from the internet.
Yes, another person on the internet was worried about planned obsolescence on those devices and whether you can use your knowledge on the hardware as well as the software to fix those kind of issues before they occur.
So I'm not sure about what specific planned obsolescence things you're asking about, but I guess on the Miele side, I haven't discovered anything that points into that direction based on the look I had at the firmware. So, yeah.
Right, microphone number 1.
Yes, with the MDU protocol, can you start cycles on washing machines they are not supposed to support? Like if you have a cheap washer, it may not support some cycles, but can you start them manually using the diagnostic interface?
I guess that might be possible because the firmware images are not different. Different devices use the same kind of firmware, but they have certain features toggled off or on based on the device model. So, yeah, I guess it should be possible to mod your washing machine to execute some kind of washing program that is not officially supported. Yeah.
All right. We have about 5 more minutes to go, but given that there's one on mic 4 now.
Thank you for the talk. How long did the whole research take you? How much time did you spend on the research?
So maybe you want to answer first.
I think I started roughly 1 year ago, but I just do it for fun in my spare time. It's just for recreation. And I think I started like 5 to 6 weeks in a row, and then maybe 5 or 6 months doing nothing because the weather was good, and then yeah.
Yeah, so for me, I started working on this in May, I think, this year, but I spent like a lot of time working on this. So, yeah.
All right, microphone number 3.
Maybe I can answer the questions the gentleman over there had about how the app gets the key. As far as I know, it at one time connects via TLS, then exchanges the key and the initiation value, and then it uses this for proprietary crypto directly connect to the device. So.
All right.
I haven't seen any proprietary crypto on the COM module. It's all standard and I think good stuff.
It's only used between the app and the module in local mode.
Okay.
All right.
I did not do research on this. Yep.
I'm sorry, I would like to continue with microphone number 3, please.
Yes. Were the temperatures pre-configured, as in you'd have like 40, 60, 90? And if so, were you able to change those values so that you could run it at, 120 degrees or something similar?
So for Miele devices, there's like a table hard-coded in firmware where those temperatures are stored for the specific washing programs. So I guess it should be possible to change the set point value for the temperature control so that it heats up to, 120 degrees. I think that should be possible, yeah.
Yeah. I think for BSH, at least with the standard dbus commands, it's not possible. But since you can write directly into memory, you can perhaps do anything. Just turn on the heater or the motor via GPIO. I did not try it.
All right, microphone number 6.
Is it possible to upload a custom melody for the program finish song?
I don't know. I haven't seen. I haven't done research on this. Yeah. I actually wanted to upload a custom picture to the Timelight projector to have some funny pictures for the kids on the floor. But yeah, that's work to do. So maybe next Congress we can talk about funny pictures and sounds and stuff like that. Yeah, would be definitely an update.
All right, and then there is There's another quick question from the internet.
Yes, the internet got a final question, which is how many washing machines were harmed or saved in the process of this research?
Yeah, you have to be a bit careful with that. If you're visiting friends and you tell them, can I open your washing machine or a dishwasher, that's they're usually not amused by this question. So I only worked with the machines we have at home and or also the things we found on the curb from broken devices. But would be interesting to have access to more of the modules and more of the machines, because that's always a problem to get the hardware for research. It's big and heavy and yeah.
All right, we have 1 minute. Number 2.
Did you find any evidence of planned obsolescence in the firmware? Devices failing at...
No.
No, okay.
From what I've seen, I can only say for BSH, it's a good engineering on the hardware and on the software side. I would buy them again, yeah.
All right, and I think with that, that's it. No more questions from here or the internet. Let's thank our great speakers again.